This is going to be the beginning of digital communication. It takes us back into the 19th century. And before there was anything on the radio like CW, there was digital communication by wire. And in the British, excuse me, in the British Empire, they built that stuff in the Victorian era by wires under the sea. So we're going to the Porthcurno Museum. You got close on pronouncing that right there. Go Porthcurno, which is all the way at the southwest end of Great Britain. You know Great Britain. You've all seen the map of that before. And if you look all the way at the lower left of it, at the end of that peninsula where there's a little red star, that is the county of Cornwall, which is all the way at the southwest end of England. And this is the county of Cornwall. And at the southwest end of that, where the arrow is Porthcurno. It's about as far out there as you can get. And it is the station from which all sorts of undersea cables came. This is kind of about the history of that sort of stuff. Let me just point out, for any of you who've not been to Cornwall, I'm moving the arrow, I think you can see it, Port Isaac Bay. Now, Port Isaac Bay, if any of you like to watch Doc Martin on TV, town of Port Isaac is where they filmed that. I'm going to move the arrow down here to Goonhilly Downs, which was a big satellite station in our day. But it, on this peninsula called the Lizard, is where Marconi did his radio stuff at the beginning of all of that. And over here at the blue arrow is Porthcurno, and that's where we're going. Porthcurno has a wonderful museum of telecommunications stuff, and that is the occasion for this visit. You can see the building up there, which is where the station was. In a cave under it is where the museum is and where we're going. And the strategicness of that location is that it was all the way at the end of the peninsula, about as far as you could shorten cables to be and have them come ashore. The map on the right, which is kind of an older one, shows all these cables going around all over the world and originating at Porthcurno. And you can go to Porthcurno and visit this museum. I've done it. I got pictures of that, and we're going to talk about that a little bit. If you get a chance to go, this is a great visit, but it is really remote when you get out there. That map I showed before will show it that it's just a couple of miles from Land's End. So, Porthcurno Telegraph Station was built around 1870, and it was the busiest telegraph station in the world because the undersea cables came in there. And this takes us back to the Victorian era. We're going to do some history things here. The first railroads at all in Great Britain were built in the 1830s, and telegraph lines were run along the railroad right-of-way. Show that in a few moments. But the telegraph lines supported the railroads, but also got the right-of-way they needed to run wires. The first transatlantic cable, talk about that a little bit. It was laid in 1858. It failed after 10 weeks, but it proved the performance of the idea. 1865 was the first undersea cable to North America that really lasted. And in 1870, Falmouth, Gibraltar, and Malta Telegraph Company built this place at Porthcurno, where it still is. And by 1900, there were 14 undersea cables covering the whole world that came ashore right there. This is the Victorian era. Just a little history. The year 1837 is very important because in 1837, Victoria's uncle, King Edward IV, died, and she was next in line for the monarchy. And this is her portrait at the time of her coronation. She went onto the throne at the ripe old age of just over 18. Now imagine the leader of your country as a high school senior. I mean, that's kind of a scary thought. But she reigned for 63 years. And the only one to exceed her finally was Elizabeth, who died about 3 years ago. The industrial age also, the revolution of the industrial age overlaps that period. And by the time of her death in 1901, a whole quarter of the entire world population was under her monarchy. So when they say the sun never sets in the British Empire, that was actually true because the monarchy with the empire was spread out everywhere and it was always daylight somewhere in there. And so there's Her Britannic Majesty. And this portrait really just shows what it means, excuse me, when we call somebody Her Majesty. Look at how majestic that portrait is. It's amazing. Um, so it's an age of technology. The Industrial Revolution really began at the same time Victoria went on the throne. Railroads, shipping were needed and they boomed around the British Empire. And it was an age of discovery. Look at this. In the USA and also in Great Britain, this was going on. This is the age of Darwin traveling around the world to develop what we would call as the beginning of modern evolutionary biology. It was an age of technological development, of industrial manufacturing and transportation. The steamship Great Western was the first steamship, the first ocean-going steamship in that age. Machinery was developed. People moved to urban centers to work in factories, engineering wonders, photography. All this stuff happens in the same period of time. And it continues into the Edwardian area. Edward was her son and reigned from 1901 to 1910. Couple of quick dates. 1837, King William IV died. I said Edward IV before, I was wrong. King William IV died. He had reigned for 7 years. Victoria was crowned in 1838, went on the throne in 1837. Takes a while to put a coronation together. First British telegraph, and look at the names. You probably recognize these names. Sir William Fothergill Cooke and Sir Charles Wheatstone, as in the Wheatstone Bridge. Somewhere or other in your education, you've come across the Wheatstone Bridge. He was the one who determined that when you reverse polarities on a DC circuit and it's an electromagnetic circuit, the magnetism changes opposite directions. Hold that thought. This became the patent on a 6-wire telegraph system, which we'll get to. In 1838, the first modern railway line from London to Birmingham. The 1831 had been Manchester to Liverpool, but it was not a modern transportation line the way the London to Birmingham was. But this is the note. Transportation and communications grew up together. Parallel in the United States, you've got Morse code and Samuel Morse going on at the same time. But I just found this picture and it really illustrates something you may have seen when you were much, much younger, when maybe some of us were old enough to remember steam locomotives. But along that was telegraph lines with lots and lots and lots of individual wires. Why so many individual wires? We don't do that anymore. But there was a time that was needed. But when transportation came up with railroads, they needed to communicate up and down the railway line, which produced another output, which was telecommunications for other purposes. You may remember, I remember seeing telegraph lines with more wires than this and lots of insulators on them, trying to follow and take advantage that one right-of-way served both purposes. They grew up together. They shared roots. They were rather short lines. They were DC lines. Sir Charles Wheatstone was the scientist, and the entrepreneur was Sir William Cooke, who did the Wheatstone Bridge. And here's their pictures. There's Cooke on the left and Wheatstone on the right. Look at them, they're as older men, but I said photography grew up at the same time. We can have photographs of it. Marvelous age. This is middle of the 19th century. And this is a simple decoder that was used on landline use. Now, you may have to look at this picture carefully to see it. But you see the 5 needles. They could rock left and right depending on the polarity of the watt power applied to them. And if you look at the screen and you look at it carefully, you can see that combinations of them and moving left and right could point to individual letters. The 5-needle galvanometer. That's why you had 6 wires. 6 wires to run this. 1 for each of the needles and 1 for the common, you could also call ground. And then Here is the chart of the combination of needle movements that indicate a letter. Um, I would have put these together, except that then the thing would be too small to even see it. I'll go back here a moment. There's the needles, combinations of them pointing to a letter. Here's the chart that somebody had to learn to read quickly. It took two operators to run this, one to look at this and figure out what the letter was, and another to write the message down. And this caused a bit of a problem to take two operators to do this, because there was no error correction and there was no way to record it other than one of the operators writing it down on a sheet of paper. But this is the earliest type of a thing we could vaguely call a telegraph in this system. Two operators were needed, one to read the 5 meters, one to figure out the letter quickly, because the next letter was sent, it was gone. You couldn't recover that. One to write it down. No way to store things except for the paper note. And once that next letter came, the prior letter was lost. But in its day, that was great stuff. Here's a refinement of that came later out of the museum. If you look at the needles, they point to letters. Still, one to read it, one to write it. And probably one could do it if they were really good at it. But that was the earliest telegraph type of communication system. Really good in its day. And then there came the need to where they're going to communicate for. British exploration and the settling of colonies, especially in South America, Central America, and Africa and East Asia, made the British Empire spread. But then when you had cables out to this, you had the issues of ohmic losses, the harshness of the seawater environment, the pressure at cable running at depth, and risks to cable as they came ashore from what might be anchors dragging, things like that. The global empire required global communications, and the telegraph did it. And the empire expanded quickly and globally during the Victorian era, all of those years. It got really big. I mentioned before, a quarter of the population of the world, a quarter of the population of the entire world was under British rule at the beginning of 1900. And if the empire got big over the years, so did Victoria. She died in 1901, but that sweet teenage girl you saw in the picture before grew into this kind of Zoftic lady. But she ruled that for 63 years. The first transatlantic cable I mentioned before, strung in 1858, failed after only 10 weeks of service, but it proved that it could be done, which is really, really important, because you always have to have a proof of concept of something before you really develop it into a better form. In that world was a man named Oliver Heaviside. He was Charles Wheatstone's nephew. He was a self-taught mathematician. He was a telegrapher. Late in his life, he went deaf. But he did something that made this telegraph stuff really, really work, and which we use for any of us who do antenna tuning. Got a tuner with your antenna and your radio, and you tune various combinations of inductance and reactance. He's the one who developed the theory of inductance and reactance. And he applied it to the telegraph theory, which made it made the whole system work out better, because ohmic losses could be lost, quality of reception could be improved by doing capacitive and inductive tuning of the cables themselves. Any of you ever worked with Maxwell's 20 equations? He also, because he was a mathematician, brought this thing down to 4 equations and 2 variables. But all that began as a telegraph operator. We talked about the operators before. He began as an operator, taught himself maths. I put the S on maths, by the way, because Brits say maths with an S, and we say math without that. But doing the British program, let's do it the British way. Cables were developed, they improved. There was an insulating product within them called gutta percha, which came from Malaysia, and it was an agricultural product. But look at these cables, how big they are, how heavy they are, because they've got to stand up to oceanic pressure and without leaking. It's quite a big deal, this development of cables. Um, and I expect a lot of that is still on the ocean floor because we've been laying cables now for 150, 170 years, haven't we? This is just a little display of cables, cross sections of them, examples of them, and how they were built. But I wish I had, there was a little ruler so you could see how big they are. Those are about 2 inches and sometimes maybe as big as 3 inches in some of the bigger ones you see. But that's what it took to lay cable and to make cable survive. We're going back to heaviside here. And if you look at this carefully, those four jar-looking things on the back are capacitors. And you can see that by pulling up and down on the little levers, you can adjust the capacitance. And then the thing coming forward is an inductor. And between the inductor and the capacitor, between the two of them, you could improve the quality of the signal coming up into, and then later on at the other end out of the cable, which really improved that situation a lot. So regeneration systems. This is the beginning of what we might want to call repeaters. There was a lot of signal off in thousands of miles of cable, and there was always the need on the part of the operators to correct errors, deal with latency. I don't know if anyone ever dealt with latency, but how much time it takes to get from one end to the other. And these systems we saw had no way to check for errors. So these semi-automatic repeaters were built. Cable repairs involved lifting from the seabed. How you fish around, find a cable, and hoist it to the surface is a big deal. Cables crossed over each other. This is still an issue with cables crossing over each other because these cables sometimes need to be repaired. So the issues that came out with improvements of these systems were better ways to send and receive. How could you store it? Remember I said before, once you missed a letter, it was gone. How do you store this sort of stuff? And if you want to retransmit something, how do you do it? So getting into those kind of issues here. This is the Thomson Cipher Reader. I wish this picture were clearer. I just didn't get the focus right on it. But it is, you look on the strip of paper, especially to the left where the light is a little bitter, and you can see the ink markings on this thing that could be used to record and receive and recover messages. See how that works? That didn't solve the saving and correcting very much because you really couldn't cut this paper and make sense out of it later. Then we got here to another reading of cipher tape, a different system. But tape reading became really important. Then we got to perforated tape. Any of you who've run teletype more than like 30, 40, or 50 years ago would remember teletype machines and rows of 5 holes in them, which were the Baudot code. And this is one of the earliest machines that cut tape. Okay, you could write a message by cutting tape and then play the tape. This is so old the cases wouldn't. I mean, this is how old this is. But it's the early use of the 5-element Baudot code. We still use Baudot, don't we? And later on, the Teletype Corporation started building this. This is from 1930. This is the Model 19 ASR. ASR stands for Automatic Send and Receive. You could receive on the machine and it would type it out on paper, the Teletype Corporation. But also you could cut perforated tape, where if you had perforated tape that you had made or cut, you could play it and send it again, which was great because if there was an error where you needed to add something to it, you could actually cut it and splice it together and then play the splice, get the word right, Ted, the spliced piece of tape. Model 19 ASR. My first teletype machine was one of these. And it was big and it was heavy and it was noisy. And because there was a lot of oil in there, because of moving parts, it tended to smell a little oily. It was kind of a pain to have in the shack, but this is how I started operating RITI back around 1980 when I was given a used one of these by someone and ultimately gave it away. Those improved over time, but if you had one of these, you know exactly what I'm talking about with this machine. The improvement was the Model 28 ASR. These came out in 1951. Um, Once again, you could receive messages, you could type messages directly, you could cut perforated tape by what it came in, or you could play perforated tape to send something out. Again, you've solved the problem of accuracy, correction, and repeating of it to send it out. These were really great machines. I wish I had had one of these. Um, until this digital stuff came, electronic digital stuff came out that we use now, starting with ASCII as the code for sending and receiving things. These were used when I was first new in the Navy. These were used in the radio rooms. They're still using them. I've seen them used up to into the 1990s. I don't think you see one much anymore, but in their day, this was as good as it got. When we run teletype and ham radio, we run it at 45 baud, which approximates 60 words a minute typing. These ran at 75 baud, which approximates 100 word a minute typing. And the type characters were moved around in a different way. But these were fabulous. I wish I'd had one of these. Let's go to the beach. This is the beach at Porthcurno. You can see from the top and the bottom of this drawing what it depicts a cliff. There's sort of cliffs left and right at the beach and a very nice beach in between them. And all the cables came ashore. You see them coming from different directions, laying down in an excavated trench to bring them ashore, and going ashore from there. And that was how that worked. Here's a picture from 1951 of a cable being brought ashore through that trench and up to a little building I'll show you in a second where all the cables terminated. Newer looking ship out there, this is good, but you can see all the work being done to bring the cable ashore, floating it, and then dragging it ashore and up to the building. And then that's what the beach does now. It's a nice beach, by the way. And this is at the cable hut where all of the cables terminated. You can actually go into that hut. I was able to go in there, and this is some of the cables. They terminated in little spots going around the wall all the way around it. You can see the sign for the Gibraltar cable number 2 coming ashore. But that's how the cables terminated, and then they ran their own lines from there up into the building, the white building I showed you at the beginning with the museum underneath it. Then there was the lady who was the docent. She toured us around inside the museum, just explaining things, showing things off. She was really very, very good. But the one thing she wasn't very good at was to telling us that nobody does Morse code anymore. They just don't do it. Nobody does Morse code. So we quickly changed that. There was a table with keys. This is if you notice that there are what looks like 2 straight keys, but they're actually the beginning of a keyer. If you read those signs carefully, the left one made DAs and the right one made DITs. It's a very primitive keyer. And then you can see that little needle in the box showing that we go left and right again. Back to Wheatstone, reversing the polarity. And the needle would go left and right. So what do? Being a CW operator, I called CQ. What else would you and I do when we run into a key? And then there back came from the CQ from G0ULY, who was also on this tour and was further down there. And I called CQ and he answered me. So while the docent's saying nobody runs CW anymore, we had a nice little short QSO there on what I'll call the audio band. While she watched this and she looked a little puzzled because somebody must have done that to her before, but we had a little audio QSO, G0ULY, and I did. Um, Using keys on this table, we could play with this equipment. So that is wired undersea telecommunications and the automation of it through teletype away from those very, very primitive galvanometers. Um, Now, on that map, I showed you that little area down the coast called the Lizard. And down on the Lizard, at a town called Poldhu, there was this foreign guy. And he was doing something communicating without wires. They called it wireless. Friends called it wireless. And he was the Marquis Marconi. He was he'd been given a title of nobility by the Italian government. Um, Giovanni Guillermo Giovanni Mario Marconi, who was the first Marquis Marconi. He was also a Nobel Prize winner in 1909, which he won in physics. And we all owe what we do to him because he was the inventor of the first practical radio as a wave-based telegraph. This is a picture of him. The undersea cable people were very suspicious of him. They didn't like that radio was coming, and they didn't like that a foreign guy was the one making it happen. But here he is at his QTH with his very primitive equipment. It all starts primitive. Now, someday people are going to look at us back here in the first quarter of the 21st century and think we're primitive. Remember that. Still undersea cable? Yes, there's a lot of it in use. The old cable probably still lays there for the lack of ability to recover it. But we now still stretch cable and we do fiber optic with it. But these are cables that are still in use. You're seeing them go all over the place. Lots of them, heavy use. If you look at navigation charts, even coastal navigation charts, if any of you do boating around here, if you look at charts, you'll see a squiggly line on the chart where a cable is, because nobody's sure exactly where it is, but it's very close to that little squiggly point. A lot of cable still in use. A lot of it being laid all the time. Because while there was undersea metallic copper-based cable, and we went to satellites. Satellites, it takes time to get up there and time to get back. Not much. But you've all heard the latency that happens sometimes on broadcast television or news reports. And latency is an issue in commercial applications, especially financial commercial applications, because speed matters on financial transactions. So there is all this fiber optic undersea cable being laid now, which is faster than the old metallic cables were, and is faster than satellite links. But we're still laying undersea cable, and the U.S. Navy still has a ship to do this, USNS Zeus, which labels these undersea cables. Lots of military uses in that. Another place where speed of the transmission really counts. So that's the background stuff that relates to early digital communications, not to be confused with analog communications, early digital stuff, the cable, the contact with the culture of railroads to share their right-of-ways, a place in Porthcurno to originate and end these cables that forwarded the British Empire, Victoria herself, and then the development of more equipment to make it all happen. Pretty neat stuff. And if you get a chance, go down to Porthcurno. It's a museum. It's open, like 5 or 6 days a week. You can get the hours if you're going to be going out there. If you have reason to go way out there, almost to Land's End, it's a long way out there. It's 350 miles out of London. It's a long way, but it is so worth the trip if you enjoy telecommunications. So I encourage you to go. And it is there's flag of Great Britain. There's the flag of Cornwall, which has its own flag as well. And 73s to you from me, G0PWW and W3TB. I'm done.